Good morning, everybody. Good evening, good day. Whenever you hear this recording, welcome to our bioinformatics tutorial. We are just going to go through a couple of concepts and we will take it from there. The first thing we should understand when it comes to bioinformatics and just biological data analysis that the principles are more or less the same with any other field. If you want to deal with biological data, you would need a database. So what you are looking at in front of you is the NCBI, also well known as the National Library of Medicine. It's our biological repository where we keep our data. Because if you think about it, when you have information, when it comes to molecular biology, this type of information look like nucleotide. And if I may type some of those nucleotide, you end up with letters like this. Understand? And this type of letters, as you know, when we get to the translation part of our molecular machinery, three of those will code for a specific amino acid. For instance, the first one is going to give you M, which stands for methionine. Understand? So, having said so, the data that you generate looks like this. Again, I'm going to type it like this, or it could take this form depending on whether you have protein or you have amino acid. And to make it easy to have this data available to everybody, what government and research institutes have done, they've created these websites that are just the front end of a large database of information. Just if you look on your left here, you see some of the resources that you can find on this NCBI. But this looks like more or less like any search website or search tool that you see. You have your search bar. I'm sure you've done most of this already in class. You can download data, you can submit data, you can develop data, you can analyze, you can do research, and even learn on NCBI. Among those databases, what you're very familiar with should be the PubMed database. This is where you get your scientific paper. For instance, if I search LACZ on this PubMed database, you're going to end up with a lot of papers, and I'm sure you covered all the filtering. But I would like to show us a little bit more of the anatomy of this website, just for a minute or two. So you get all your database there. You can choose to do a search on a specific database, or you can run your search on just the full NCBI blast. But what we are very interested in is if you're running a search just generally without looking at a specific database. I'm going to look for this gene, which is HSP90, which is a heat shock protein 90. If I run this keyword across all database, what I have in front of me now is a result, and there's numbers highlighted in blue, tells you how many hits with that specific number you found or are found in the specific database. If I was looking for a paper, then I'm going to find the PubMed at some point here. If I'm looking for genes, this is the gene, the category of all the gene pool dataset, protein, clinical information, genomes, and chemistry compound. All right. But let's say I'm interested in the nucleotide here. If I go to the nucleotide, I'm just going to do right click to open this tab somewhere else, and I see that I've got a lot of those and I need to look at this one. So this is our tutorial. I want us to understand how to read and how to interpret this type of information. Okay. So when you have a page like this is giving you important information about the nucleotide sequence of a specific gene. And when looking at this gene, for instance, what you would notice is that you have the name of the species the name of the gene and what it is. So it's telling you that this is a complete CDS. I'm gonna get to CDS just now, but you have an option here to look at the graphics or to look at the FASTA file. Let's just open both of them for a second here and see what is going to happen. When you choose graphic, because this is more or less a complete region of a gene, from the graphic it's telling you this is your heat shock protein 90, this is your mRNA, and probably this one at the bottom is going to be again the exon, the part that is actually going to give you the protein. This is fine, but for now it's not really our primary mode of interest. We're going to look at the FASTA file. So when it comes to FASTA file, it's just a format that we attribute to nucleotide on a computer. If you think about it, when we talk about music and sound, we've attributed some formats to them, such as .mp3 and .wave. If we look at document, like your assignment, we've attributed some format into them, .pdf, .doc for Microsoft Word. If you look at videos as well, we've assigned some format or extension near them, .mp4, .flv, and so forth. Okay. Now, a FASTA file is just an attribute, and the anatomy of a FASTA file is very simple. You need a greater than sign, you need a title, and some reference number, and maybe some information about the sequence. Then on the next line, you put your nucleotide like this. And after you've done this way, you have a FASTA file. Just like with a Word document, you need a blank page and a couple of words in it. With a FASTA file, this is all that you need. And if you want to create one, all you do is you come to this in your notepad, save as, and quickly just change the type here and call it my sequence. I'm just putting my sequence 1 and put a full stop, and do not forget to give it the extension .fasta, and you press enter. Now if I were to go to my file to find that folder, which I'm going to bring to you just now, you see that my seq1 is telling me that it's a FASTA file, and in fact I can even open it with one of the softwares that I have on my computer that deals with FASTA file. And this one is still a text document, as you can see, and the rest are FASTA file. And if you would like to fetch a FASTA file on your computer, all you have to do from the internet, highlight the sequence. As you can see, you have the sequence and the greater than sign plus the title. Copy this and bring it to a notepad. Let's just create a new blank one. You paste it this way, and as you can see, we can just call it now file, save as, change the type, very important, and call it HSP90 gene dot FASTA, and you press enter. Now if I were to come to my file here, if I refresh, what I'm going to see is my HSP90 gene. If you still have doubts, I can open it with Bioedit, which is one of the tools where we look at biological data. You see that my sequence is there, and hopefully I can highlight and do a couple of things with them. Alright, so that's how you create a FASTA file, and that's what a FASTA file is. But if you think about it, this is a complete CDS, as it's saying that it's a nucleotide sequence that eventually is going to give you a gene, which means that inside this sequence, which let me just open it here, I have information to make a gene from my nucleotide. But from moving from DNA, RNA, and protein, it's not the full DNA sequence that is actually going to give me my protein. we need to get to an mRNA first, where we need to have a start and a stop codon that is going to help with translation. Having said so, what you notice is that usually within a nucleotide, it's a portion of sequence like this in the middle that is actually coding for the actual protein or the actual gene. Okay, and this region that has a start and a stop codon, we usually call it an open reading frame, or ORF. And again, the way we refer to this region again that actually codes for the actual gene, usually on this website such as this, we call it a CDS region. So it's just a region that is an open reading frame. Now let's go back to this page and see what else can we get from here. One of the things that you get from here is you will notice that you have the locus. So that locus is just the reference number that has been attributed to that website, and probably the date where it was uploaded, and you have this 2635 BP. So this is the length of your nucleotide. Please remember that nucleotide, the length is always in base pair, and with protein files, usually we talk about, excuse me, amino acid. Your accession number is here. So this accession number is the number that we need to get and save as a reference file should you want to get back to this file later on in the future. So I'm just going to save this reference number here, and this is the version 1. Give me a minute. Now, if I were to select this accession number for a minute, copy it, bring it here. If I go to NCBI again, instead of searching for H-shock protein, if I'm NCBI, all I could do is just paste this reference number here, and you will see what's going to happen. It's going to land me straight with just one hit or two with the nucleotide file. And if I click on this nucleotide file, I'm going to land on this page again. You see it has made it very easy for us to get back to the sequence, because if I were to search HSP90, I'm going to get all of this, but I'm not after all of this. I just want the first one. Moving on, you have the source, the name of the organism, the authors, and titles. Was it published or not? Which journal was it published on? And all those type of metadata. But you also have feature and source. With features and source, it's telling you a little bit more about the sequence. You have the name of the organism, it's a genomic DNA, the taxon, but they're telling you also about the gene, mRNA, and your CDS region. Most of the time, those three values should be the same, but there could be differences in some instances. But if you'd like to know which region is actually coding for the gene in this nucleotide, then you have to rely on the CDS number. So as you would notice, the CDS number is 113 to 2,278. And the way you can spot that is looking at the nucleotide file. This is still the same nucleotide file here, but they've made it easy for us to count the position. So this one stands for this, position 1. This is position 61, and this is 121, and so forth, 2,581, until you have your last one, which is 2,635 up on top here. Okay. Now, this file is telling us that the CDS, the region that actually code for something, is 113 to 2,278. The easiest way to find it is you look at this position number reference, and if this is 128, all you have to do is work your way back like this to actually spot 113. And the same thing applies for 2,278, so you look for 2,000, maybe 281. If this is 2,281, to find that you need to work your way back. But you may ask yourself, why is this information important to me at this specific point? The information is important because should you want to design primers to actually make this gene, by the way, this is the actual protein file, like the output that we could get from 113 to 278, they're already given us here. If you want to design primers, then what you'll be interested in will be to actually look for your coding region like this and create primers. But once you're creating primers, let me just open a new Word file. I'm just going to show you something quickly. Now, let me just open this new Microsoft Word file and explain what is going on here. If you like to create primers, I'm going to take these values and bring them here for us quickly, and I'll paste it here. Let's just alright, I have my file here. If I want to create primers, because we don't really have time with this recording, I have class straight after this which I need to prepare for, but you can do it in your own time. Let's just assume that you've managed to spot these two positions, 113 and 278 from this file. And to do that, as I told you, just find one position and count back. And if we come back to our Microsoft Word document, you know exactly where that region is, and just for argument's sake, I'm going to say maybe that region is somewhere here, which I'm going to highlight in green instead. So to make it more realistic, let me leave out this and let me leave out that. So this region in green is your actual CDs, your actual information that is going to create the protein. If you want to make primers, remember with primers, you're trying to amplify a gene, not necessarily a nucleotide, but you're trying to amplify a full gene. So if you want to design primers, what you want to do is to select the primers that should be a few sequences before your coding region and a few sequences after. That one is going to be very important because it's going to help you actually not miss any of the important region in green here. And as you understand, if you followed in class and all the explanation that polymerase, when it starts to read, it's not always accurate. It could be shaky from the sequencing machine. So the few base pairs that are read from the beginning are not always accurate, and the last ones are also not always accurate. So to make up for that and ensure that you actually have a very good amplification, you want to give your primers sequences that are a little bit outside of this region. So I'm not going to go through this video, but be aware of the criteria selection for your primers. The length of the primer, you need to have between 18 to 20, it varies, some people say 15 to 24, but I think you get the pictures. 18 to 20 base pair sequences, that is really good, and you need to choose a very good melting temperature. I think probably above 55, and your GC content should be between 40 and 60, and you understand why we care about the GC content in the beginning to begin with first, because GC content is all about the strong hydrogen bonds that we want to melt when we're opening and closing the strand during amplification. Now that you know this and you're aware of all the criteria for primers, let's just say that you select this region, this few sequence before here. I'm going to give it a color blue, and you select this here, and I'm going to maybe give it color purple. So these are your primers. Now you see the way you've done it is that you can call out these bases, be aware of the direction. We're moving here from 5 to 3 prime and 3 to 5 prime in the reverse, and you see that polymerase can start off here, read a couple of terrible base pair maybe, and start here with your actual sequence, and on the reverse side it's going to do the same thing as well, and you have your full amplification. This is really good because at this point you are actually sure that you have the sequence. And another thing that you can also fetch from this page is it'll be easy for you also to have an estimate of the actual size of your mRNA. And how do you do that estimate? If you know these two numbers, position 113 to 278, right? As soon as you're aware of these two numbers, it's easy for you, which is that to do the math quickly and actually get the estimate of how long is this thing. So let's just do it live. I haven't tried it yet. There we go. So if you do the math to know the actual length of this region, you're going to do this minus this. Of course, you have 2,165 base pair. That's the length of this green region here. And from this region, you can also get an estimate of how many amino acid I'm going to get, right? Because you know by now that to get an amino acid, you need one amino acid. Here is equal to what? Should be equal to 3 of your sequence, of course. And I'm sure by now you're already guessing how I'm going to do it. But there's one thing that you need to remember. In this region in green, just for argument's sake, this is not the actual start codon, by the way. Let me just put it in yellow. You have a start codon, and in red here, you are going to have also a stop codon. By codon, you already know that we're talking about 3 nucleotide base pair. So you're going to have your start and you're going to have your stop here. But if we think a little bit again with our scenario, what do we know is that your start codon, your start codon is equal to what? Is equal to AUG, which in nucleotide is going to be what? T, which is equal to TAC, and of course AUG that side gives you what? Methionine. Makes sense, right? But when it comes to stop codon, you have what? I think the way we did in class, you are annoying, you go away, and you are gone. That's how I remember it, at least. All of this does not give you a specific amino acid. Those are just stop codon. If you like to figure out how many amino acids you're going to get, the first thing that you need to do, you take this number 2165 base pair at this minus the stop codon 3 base pair, then you end up with 2162. Understand? Because if I do that one, I think minus 3 base pair, you end up with this one. So to know how many amino acids you're going to have, I'm sure you can scream it out loud by now. You're going to divide this by 3, and the numbers are not correct because we just chose a random number, but let's just settle with 720. Okay, so that is how you could get the actual number of amino acid. And since you've got the number of amino acid, what you may want to know as well is the size of the protein. To get the size of the protein, the estimate is usually that one amino acid is approximately about 100 EA Dalton. Okay, so if one amino acid is equal to approximately 100 DA and you have 720, all you need to do is, can't believe I'm using a calculator for that, but let's just show us, all of us, like this. So you see what I did there? 720 times 100, and that is going to give you 72,000 Dalton, and you may want to just shorten that and put it in kilodalton by dividing this to 1,000 like this, and you see that your protein would be about 72 kDa. Now, at this point, you're like, okay, I get it, but why do you even need to work out this 100 in kDa? You're doing amplification, you may want to do protein extraction. With this value in base pair, will allow you to spot your gene where doing gel electrophoresis from the ladder, for instance. And with this value, when you are purifying your protein, you could look at the protein ladder as well and look for any band in this specific region. Okay, I hope that this really made sense, and maybe we're going to use another 2 or 5 more minutes to just introduce BLAST as well. Well, NCBI BLAST is one of those very interesting algorithm. So if you just go on the internet and search NCBI BLAST or BLAST, there's a high possibility that you're going to land on this page. BLAST. So BLAST stands for Basic Local Alignment Search Tool. And of course, there's a nice definition here: finds regions of similarity between biological sequences and all that. But now, at some point, what you can usually end up with is that you're going to have a sequence that you don't know the origin of, because let's just assume you are a medical scientist / doctor and all that, and you have patients that are coming to you with some complication, running stomach, and they're just bleeding all over the place, and you don't really know what to do. But you remember that there's this gene, let's say that we call the 16S, ribosomal 16S, which is universal to every single bacteria, and you can sequence it from even in a non-bacteria and get that sequence to identify. So the good scientist and doctor that you are, you send your sample for sequencing, and when the sample came back to you, which as soon as they do, they look like this, a chromatogram. Let me see if I can quickly get you a chromatogram file. They will look like this. Just give me a second. They will look like this. You have this chromatogram where, as I told you, you see this is supposed to call nucleotide, but the very first base pairs are quite wrong, because we don't have a nucleotide. W stands for nothing, but somewhere in between you manage to do like a good call, as I told you. So towards the end is always messy. After 508, the frequencies are really low. But you saw this one from sequencing as well when we studied it, that we usually get our file as a chromatogram, and the highest peak you make a call that this is guanine, adenine, and all that. You did all of that, and eventually what you landed with was the sequence, like this. But in all honesty, this is just data, this is information, and you cannot really tell what this is just by looking at that. Maybe let me paste it in a notepad to make it easy for us. So you just have this. You don't know what it is, you call the nucleotide, but you need to find out what it is. And just like music, I like using this analogy, it has happened to most of us. With technology, you go to the supermarket, you go to a public place, and you hear this very nice song, very nice guitar line and piano, and it's such a beautiful voice, but you don't know who sings that song. And what do? You reach out to your phone, and there's this app that called Shazam. You just double tap on it, and it's just the last 40 seconds of the song. You're reaching out to your phone, switching on data and all that. You manage to press Shazam, and just with that very last fragment of the 40 seconds of your song, Shazam was able to record it, run that piece of melody to its internal database, which is linked to what? Spotify, Apple Music, YouTube Music, and whatever, and it gave you a nice feedback, hits back that this is a song by, I don't know, Freddie Mercury, Bohemian Rhapsody. You're like, oh, this is a nice song. Understand? Now, of course, with sequences, it's not as glamorous and fun as Shazam maybe, but you have patients and people are dying, they're showing some bacterial infection symptoms. All you have to do is that have the sequence. It's also not a sequence from the entire species, just the last fragment, but that can allow you to do ID. So this is where BLAST comes into play. It's a basic local alignment search tool. So what it's doing is that it's running your sequence in a specific database, and it's going to align it to every single sequence that exists there to give you some feedback so you could have an idea of what you are looking at. So let's just click on it. So you can blast against nucleotide sequence, protein sequence as well. Or you can blast your protein sequence to find the nucleotide, and the other way around as well. But for this scenario, we're going to click on the nucleotide blast. Once you click on the nucleotide blast, there are a couple of options, but for you, you are in a rush, people are dying in your hospital, all you want to do is just find out. You can put an accession number if the file were already deposited, or a faster sequence, or just copy a sequence like this and paste it. As soon as I paste it and I click blast, I would like to show my result in a new window. It's going to take hopefully a couple of seconds or maximum a minute or two to actually do the blast. So right now what you see is that this computer is running through all the NCBI database just like Shazam, and just as fast as Shazam, surprisingly, you have a couple of results. Now what you are looking at here is the result. It's telling you what are the hits, and like the music analogy, which I'm going to stop with it now, you get only one song. This one gives you a couple of options. But how do you interpret them? The first thing here on your right is the accession number. You saw how it works, you just need to access something. This is the actual length of the protein where it found the highest hits, assumingly, and goes from highest to lowest. And you have percentage identity. So with percentage identity, let's say this is your sequence ACCC here, and in that database, if there was also a specific match like that, like AACC, AAGA, T, and CC, that's 100% percentage identity. If there something was missing like this, or instead of T here you had an A, the percentage is going to change. But I think by now you get the picture. That's how you get to percentage identity. In fact, it should be called nucleotide identity, but that's all right. The coverage now, let me just move to coverage quickly. With the query coverage is, if your sequence is, let's say, this long, let me just remove this part, it's this long, and it found it was matching, but at some point, it couldn't cover the whole sequence, or it only covered like a few sequences of what was in the database. So this is your query, what you submitted, and this is what is on the database, right? So now, if it's covering the full thing, like let's say it was like this, then the query cover is going to be 100%. If something was missing, then the coverage is also going to change. I hope you see, you get the picture now. The e-value, this is just a statistical value that this was not a mistake, and how many times, the chance of having a mistakes and all that. It's more complex than that, but that's what you should understand at this point. But what you need to know about e-value, 0 is a good number. It means that the chance of having this being random and being an accident is actually 0. So with e-value, the lower the better. With query coverage and percentage identity, the higher the better. Max score and total score, we also call them as bit score. It's also a very complex statistic analysis here, but most of the time, the higher the bit score, the better as well. So after you do this, you see that I'm matching nucleotide per nucleotide, nothing is missing. As a result, you're like, okay, the species name that I'm getting here, just like the song name, is Didymela glomerata. Then you know, okay, that specific bacteria that it goes in trouble at my hospital is called Didymela. That makes sense. So this is actually how you could use Blast to read, and you also have a graphical summary which is showing you about the coverage. But you see, most of the sequences here are actually red, which is good. It's covering greater than more than 2,200 base pair. You have an alignment. You can actually see the actual alignment from your query and what's on the database for every single sequence. You could also look at the taxonomy to know where this thing is standing, and the description, we already looked at it. And if you like to download that sequence as a FASTA file, you can also just click here and choose how to download them. When it comes to designing primers, you can use Primer Blast and work on that. But at this point, I'm really running out of time. I'll show you there are a couple of ways of doing this. So now that you've looked at the sequence and you're like, okay, I know what's going on here, and I'd really love to design more primers to amplify that region. And all you have to do is that as soon as you understand the principle of primer design, which you should look in your pack note and all that, you set your specific melting temperature that you are looking for just as a window. All you have to do is just click on primer design here and give it a couple of seconds as well, and it's going to do that. But while you're doing primer blast, there's also something that is not in your books that people use as well, is this other tool called Snapgene. It's usually free for a month, so if you want to play around with that, you can do. But if you have a faster file, you can choose to open it with Snapgene. And I'm just going to do it quickly for us and show you how this one works while we're running our primers here. So what you usually do with Snapgene, as soon as it opens, if you have a gene, you want to open it in linear. If it's a plasmid, circular. But this is very important also with plasmid restriction enzymes and all that. But you recognize this, some of them are familiar, like IND3, you know already that this is just a restriction map. But when you go to sequence, there's a quicker way of designing primers using this tool as well, and most labs nowadays, they also use this. As you can see throughout the sequence, it's showing you the potential restriction enzymes and the type of cuts, palindromes, sticky ends, blunt cut, and all that. But let's say you know that your open reading frame is somewhere here, which I can just give it maybe a green. This is my open reading frame in green, you know that, and my stop is somewhere here. I'm just also going to assign it color. Let me just give it a red color, for instance. Okay, primer blast is finished, but let's just do this. So once you have this, the same principle applied, this is your CDS, you want to design primers before. But with these new recent tools, all you have to do is just highlight, and you see as I'm highlighting, it's giving me some melting temperature already, and I can see I've got 20 base pair, melting temperature of 58. I can just let that one go and come here, add primers. I'm going to choose my top strand because it's my forward primer. As you can see, I actually have a nice primer there that has been designed for me with a melting temperature, and I also have my GC contents there. I can call it primer 1, I'm just going to leave it there, and add primers. Then you have primers. For your reverse, you can also do the same. I look at my melting temperature, I'm very happy. 21 base pair, okay, 20 base pair. I can also let that one this way. I should add primers. Bottom strand, of course, the GC content is 40, and I add primers. So this is one of the easy and quickest way to add primers as well. But you also have the primers on this one. So this is nice because you get a couple of options. You also get the self-complementarity, which is really important. The lower the better, otherwise the primers are going to fold on itself, and you can see the sequences. And now with this one is that you look for your open reading frame, and what you want to select is the longest option because you want it to cover your entire sequence. And if it's still not covering, you can play around with the values until you actually see that this is covering the whole region. All right, so this was a very short introduction on bioinformatics, unfortunately, but I really hope that in the future we will get to have more, because there's actually a lot more that could be done with such a broad topic. But thank you so much for sticking up to this time, and all the best with your test preparation and all that. And I wish you a wonderful day. Thank you. Bye, everybody.